Welcome to the National Science Foundation. I'm Josh Shamit. I'm here today with Margaret Murnane and Henry Kapteyn, both of the National Science Foundation Engineering Research Center for Extreme Ultraviolet Science and Technology, and also at the University of Colorado, and also at JILA, a unit of the National Institute of Standards and Technology. They're joined by Research Associate Tenio Popmintchev, the lead author on their upcoming paper that's going to be coming out in Science on Friday, entitled Bright Coherent Harmonics in the KEV X-ray Regime from Mid-Infrared Femtosecond Lasers. In the paper, they're describing a new technology for creating laser-like beams of light that simultaneously stream UV light, X-ray light, and all the wavelengths in between. This is the first tabletop setup to produce such a coherent beam of X-rays amongst the others, and the technology could achieve pulses as short as attoseconds, which are quintillionths of a second. Which will enable the researchers to ultimately observe some of the fastest processes in nature, theoretically things like watching electrons going around a molecule. Some initial housekeeping. This is being recorded. We'll have a copy available for everybody about close of business today. The research is under a strict embargo until Thursday at 2 p.m. Eastern Time. But you can ask questions at any time. Just send them to webcast@nsf.gov. If you are on the line and wish to ask a question by phone, just press *1 and we'll immediately put you into the queue to ask your question of Henry, Margaret, and Tenio. And so with that, Margaret and Henry, tell us a little bit about this new technology.
Okay, Josh, our advance gives us beams of light in the X-ray region of the spectrum that have properties of a laser beam. Essentially, it gives us an X-ray laser on a tabletop for the first time. And as many of you know, X-rays are part of the electromagnetic spectrum, just like light and radio waves. But X-rays have wavelengths 1,000 times shorter than what we make use of to see. Laser light is coherent, meaning that it's in the form of a directed beam that's highly focusable, and that hasn't been possible in the past with X-rays.
And the way we do this, Josh, is not simply to make an X-ray laser. It really is not practical to make an X-ray laser on a tabletop. It simply takes just far too much power at short wavelengths. So instead, what we do is we take an existing infrared laser and convert it to wavelengths that are 5,000 times shorter. So Henry mentioned that light is a wave, an electromagnetic wave, but you can also think about light as in the form of photons, which are packets of light energy. X-rays with short wavelengths have very high energy photons. They pack a lot of energy per photon. Infrared light has a long wavelength and a very low energy per photon. But what our process allows us to do is efficiently add 5,000 low energy infrared laser photons to make X-ray photons.
And to accomplish this, we actually went back to the physics at the very origin of X-rays. So X-rays were first discovered by Wilhelm Röntgen in 1895, and to make these X-rays, he used an electron tube that slammed electrons at high energy into a metal target. What we've done in our technology is develop an understanding of how to use lasers to drive this same process to generate X-rays, but to do it in a way that also maintains the coherent, the laser-like properties of the X-ray beams. And to do that, we take a fast pulse of infrared light, one that lasts only a 10,000th of a billionth of a second, and focus it into a high pressure of gas. Just like when you pluck a violin or guitar string very hard, you hear lots of harmonics. And those harmonics are at higher and higher frequencies that are related to the original starting frequency. That's, in this case, the starting frequency is the laser frequency, and the harmonics span all the way up to the 5,000th harmonic, which is in the X-ray region of the spectrum.
So the specific challenge we were able to solve is how to make this process efficient. Now, if you want to get a bright beam of X-rays out, what you need to happen is that every atom in the medium is emitting X-ray waves that add together constructively. So as the laser moves through the gas, a high-pressure gas, it plucks an electron and then violently slams that electron back into the atom, and both the laser wave and the X-ray wave have to travel through a high-pressure gas at the same speed. No one thought this would be possible, but fortunately we were able to figure out how to do that.
And by high pressure, we mean pressures as high as 40 atmospheres. For example, just as a comparison, this is the pressure a quarter of a mile below the surface of the ocean.
Wow. And what is the gas that you're using? We got a couple questions from Jesse Emspak, and one of the first ones he asked is what is that gas which is being used in the waveguide?
Simple helium gas.
Just helium, okay.
Yep. We actually, one of our findings was that, quite contrary to what had been the understanding in the past, in fact, this process favors light atoms like helium. And by making that change, and by also understanding that we had to go to these very high pressures in our interaction, that's where we really saw that we were making this process work optimally, and we were getting very nice beams of light out.
And the nice thing about the X-ray converter cell is it fits in the palm of your hand. So it's a very small device.
And that's the waveguide?
That's the waveguide. That's okay. Right, not the laser. The laser fits on a desktop or a tabletop, but the X-ray converter that you see here in the image is really just a little bit bigger than a green laser pointer.
So within that chamber, the gas is contained at these pressures of several hundred atmospheres or several atmospheres?
Yes, absolutely. And so Tenio had to take a lot of care to make sure the engineering was done really well, because right. Pressurizing something to 40 atmospheres, you want to be careful that you do that properly.
Yeah, you don't want to drop anything on there.
Yeah, and the other technical challenge was that we actually have to make a transition from these high pressures into vacuum to propagate the X-rays to our experiment. So we had to learn how to deal with very high pressure differentials.
So at one part of the machine, you've got this 40 atmosphere pressure, and then immediately following, you go right into a vacuum, but yet you don't suck the helium out?
We do, but we made sure that we do it in a way that we can continuously flow the helium.
Wow. Is that a trade secret, or is that something you can describe?
Well, it's fairly straightforward. We're putting gas in, and because we use a waveguide that both guides the laser light and also contains the gas, that means that the aperture through which the X-rays emerge is exactly the same aperture that the gas comes out, and that allows us to limit the gas flow. It's a very small beam, it's a very small hole that the gas can flow through, and we just have developed a system. Actually, Tenio is the one who developed that system to do the gas handling.
That's great. So when this beam is coming out, how many molecules of helium could fit within the exit point of the beam, just out of curiosity?
Oh.
Not that you have to do the calculation in your head, but are we talking like tens? Because you're talking about very small
Margaret,
wavelengths.
Tenio, do you have a guess on that?
So it's
thousands, I believe,
if not millions.
Yes.
So.
Okay.
Yes.
So it is quite a few, but it's contained enough that you can still get the results you're looking for. Great.
Yes.
Okay, cool. Well, let me turn to a couple other questions that Jesse sent, and then we have some that came in from Neil McDonald at Federal Technology Watch that get more into the business angle of things. But the first one, and the one that everybody's been asking, is to get a little bit more into the applications. You mentioned some that we have in the world of imaging, and maybe you can get a little more into what we would see with this type of beam and what that means, whether we're getting a data set on the other end or whether we're actually getting a picture on the other end. And we have a couple of the images that you sent of the profile, so we could bring those up if you need them. And then what does it mean for other areas of research, giving, especially, he says, especially given that it seems that X-ray lasers through this breakthrough can now be made tabletop size. So what is it that we can see in terms of applications from the science side in terms of imaging, and what does that mean in terms of now having something that's tabletop as opposed to the size of a facility?
Yeah, so the immediate application that we see for these tabletop X-rays is to understand how the nano world works. As you know, nanoscience and nanotechnology involve very, very small objects. And to view them in a microscope, you need a wavelength of light that's comparable to the dimension of the object that you're looking at. And nanotechnology over the last 20 years has moved to objects which have size much, much smaller than visible light. And that limits your options for how you can see what's going on, how you can see dynamics, for example, in a nano system. Our X-ray wavelengths are 1,000 times shorter than visible light, which means you can use them to see very small features. Another big advantage of X-rays, in particular an advantage over electrons, which is electron microscopes are used in nanotechnology, but X-rays can actually see characteristic absorption edges that allow you to identify particular elements, for example, silicon versus copper versus aluminum. Or in a molecule, you could have a molecule that contains several elements, and you could use the X-rays to follow how the molecule is reconfiguring or how electrons are traveling through the system.
And what does that final picture look like? I mean, when you say we see it, I mean, some of us are used to optical microscopes or a tunneling electron microprobe or something like that that would give us some visual picture. Is that what we're expecting here, or is it more a informational data set that comes out that we then interpret to tell us what the thing might look like?
In some cases, it is a picture. Okay. So we have used these beams to generate images, and we've gotten, for example, semiconductor companies and some of the companies that make the hard drives that go into your laptop interested in this technology. Other times we're looking at specific spectral information or information on acoustic waves. So there's a variety of different methods by which you can use these beams, and there are a variety of different types of systems that you can look at. You can look at nanosystems, you can look at molecules, you can look at dynamics of sound waves in materials.
So now that it's tabletop, you know, you're talking about, now you're bringing in some of these other applications. Let me get to Neil's question, because this tabletop brings in the fact that these other companies are now looking at it as opposed to it just being a research effort. And Neil mentioned, let me get to his question here real quick. He said, it's easy to understand why scientists will be excited by this development, but what could be some of the tangible applications or impacts for industry, such as in the telecommunications sector? So he's thinking even beyond the imaging aspects, but to just how lasers are used. Do you have any ideas? I know that's a little early to be talking about those applications, but I know that your femtosecond lasers and other devices are being used by companies for some interesting things. So what would be the future for this type of system?
Margaret, you want to?
Oh, okay. So, for example, you know, when you put your laptop on your lap, sometimes actually it's too hot to do so. And that's because really people don't understand how to design circuits so that a lot of the energy isn't wasted as heat. And so one thing that some of the companies are interested in doing is using these X-ray beams so we can understand how heat flows in nanostructures, or how fast can you flip a magnetic bit for data storage, or how can you design a more efficient catalyst. To design, you know, catalytic processes happen often with electrons hopping from one part of a surface onto something on top of the surface, and that electron can move incredibly fast. on order of a femtosecond, which is a millionth of a billionth of a second. And only these X-rays are fast enough to catch that electron hopping. And if you can't see what's going on, it's very hard to understand what the science, and it's very hard to design more efficient devices. And so a lot of the applications of these X-rays that we see coming up will be, for nanometrology and understanding and optimizing nano devices. But then, it's not at all clear what the limit of this technology is. We certainly don't understand the limits. Now we don't see any limits. So in the future, it may even be possible to have, a directed pencil-thin beam of hard X-rays that can be used for medical X-rays. And the fantastic thing about that would be that instead of the sort of blurred X-ray image that your doctor looks at now, and that sometimes, we wonder how on earth are they really seeing as, so much, getting so much information from those X-rays. If we could take an X-ray image that was as crisp as the wavelength of the light used to make that image, and that would be a big advance in medical science, medical applications.
Absolutely. Cool. All right. Well, then let me bring up another question we got from Innovation News Daily from Francie Deep. And she's asking, what's the benefit of having several wavelengths in the laser beam instead of just X-rays? And maybe I'll throw that one to Tenio.
For example, here we have extremely broad spectrum spanning from the ultraviolet up to the X-ray region of the spectrum. And typically in medical devices, you have also a broad spectrum, but this is more towards the hardest X-ray region of the spectrum. Here our devices, we have not reached these wavelengths yet, but as Margaret mentioned, we don't know the limits. The advantage here is that we can observe several several edges of different elements simultaneously, and we can tell simultaneously not only what kind of elements we have, but actually determine, study the dynamics in molecules or in atoms.
That's great. And
yeah,
go ahead, Henry.
Yeah, another very important aspect of having a very broad bandwidth is that broad spectral bandwidth is linked to very, very short duration light pulses. You need a very broad spectrum to make a short light pulse. So this is the broadest coherent spectrum of electromagnetic radiation that's ever been created. It also corresponds, if we can understand how to use it effectively, it also corresponds to a light pulse that could be as short as 2 attoseconds in duration. And an attosecond is 10 to the minus 18 seconds. It's about the time it takes light to cross the distance of a molecule.
Wow. So
this was very,
go ahead.
Sorry. Thanks, Josh.
Sure.
This was very surprising because as a result of this research, we discovered that actually nature wants to make these incredibly fast bursts of light that really are the ultimate strobe lights, because even electron motion, on a photovoltaic or a catalytic surface are frozen on this time scale. So it really is the ultimate strobe light.
Wow. So if we're talking, femtosecond is 1 times 10 to the negative 14th seconds. Attosecond is 1 times 10 to the negative 18th second. And you're getting these shorter pulses, and you're telling us it's because nature wants you to. But how do you actually generate them, and explain why it is that these pulses are the end result? What's happening in the process that it comes out so quickly? It's not like you're flicking on the switch and flicking it off very quickly. So what's actually going on there?
Actually, nature even may want to make even shorter bursts. Tenio's latest paper has zeptoseconds, or 10 to the minus 21 seconds in the title, which is 1,000th of a billionth of a second. So it's quite amazing. Henry, do you want to explain, why the bursts emerge so quickly?
That's a difficult one to explain, but I can give it a chance. It is actually also related to the fact that we generate such a broad spectrum of light. And
So,
I don't know.
so maybe I can jump here. So in here, so Josh, so so it's how these X-rays are generated. You know, we made the analogy that, you know, when you pluck a violin string, that harmonics are of the sound, the fundamental sound frequency are generated. So now we use a light pulse to pluck an electron bound to an atom, and then violently crash that electron back into the atom. And the X-rays are emitted only while that electron is being violently smashed back into the atom on each cycle of the light wave. And so the bright X-rays emerge only over part of the light pulse, because of this need to add together all the X-ray waves constructively. So again, this is, you know, related to nature really takes this relatively long laser pulse that could be tens of femtoseconds, but the X-rays are emerge only during a very small part of that light wave. So nature just helps us to do that. And so just by focusing the laser light into the high pressure cell, what we get out is a 1 femtosecond burst of X-rays. And those X-rays are chirped, just like when you hear a Doppler chirp on a train when it's moving towards you and then moving away. But there are ways to reconstruct all the waves and make the light pulse, the X-ray burst, very short.
So it's really the snap. It's the snap back
It's
of
snap
these electrons,
back,
and
exactly.
it's the if you get your energy right, you get that snap to be really quick. And,
Yes.
and okay.
And the need for X-rays from many atoms to interfere constructively automatically selects only a small part of the X-ray burst in time. And then, so that's where nature comes in, helping us a lot.
That's
Yeah,
great.
and I would add that it's going to take us quite a while to understand how to use effectively a light pulse quite this short. Certainly in the short term, there are applications where we would look at, for example, how the molecules and the atoms in a molecule rearrange during a chemical reaction, where now we have plenty of time resolution to look at that even right away.
Now, can you get the beam to go longer than that, or get it to repeat so that you can continue to view what's going on?
Yeah,
It's basically a snap, so can it snap and snap and snap?
the normal way that you use these very short laser pulses in the lab is very much like people use strobe lights. So what you do is you have a process that repeats itself, and you can trigger it with one laser pulse and then use the X-ray pulse to take a snapshot at some time, just a few attoseconds or femtoseconds after you've triggered the event. And then you just repeat that, changing the delay, and you make a movie of what's going on in the system.
That's
with
fantastic.
extremely high time resolution.
So you could have movies based on these electrons just going across as they're going through the monitor. That's fantastic. All right, let me get to a couple questions that came in again. Another one from Jesse, MSPAC. This one is interesting because of the way we're talking about these very quick pulses and the scale of what we're talking with the tabletop system. But he asks, could a tabletop system like this be used to generate the kind of high-energy laser pulses that were discussed back in the Star Wars program? And Star Wars here, obviously you guys will know this, but we're talking about the program back in the 1980s to shoot missiles down.
Yeah, I'd love to answer that because that question brings an interesting history. In fact, the first experimental efforts to develop an X-ray laser were done as part of the Star Wars program, where they did a number of nuclear weapons tests. They were using atomic bombs to generate enough power to make an X-ray laser. And a lot of the details of that work are classified, but I believe that in fact in our work now, we're generating X-rays with photon energy in the same range that they were able to generate back then in the 80s with a bomb. Of course, for science, blowing up your lab every laser shot isn't a good idea. So you have to develop more practical ways of doing this. Another distinction that you have to make is there's two kinds of energy here. There's the energy inside an individual photon. That's very high for any X-ray. But then there's the amount of energy that you get in a single pulse of light. And our tabletop device does not generate pulses that are useful for destroying missiles with.
Right.
So maybe another way to put this is we can only get a certain fraction of the laser power converted to X-rays. So we start with a laser that's very modest. It fits in a lab. It generates maybe 10 watts of power, which a 10-watt light bulb is not super bright, but we can convert that 10 watts of average power, but we can convert a good fraction of that to X-rays, which are fine for illuminating a microscope or following charges, in circuits or understanding how magnetic materials work.
So you're not going to be carving things up with this device anytime soon either?
Except for nano objects. We can blow up molecules, no problem.
Right.
Yeah.
Great.
One
go
has to keep in mind that the conversion efficiency of laser light to X-rays that we've demonstrated is optimum now. We can do as well as we think is physically possible, but it's still a very small fraction. It gives us a beam that's very useful for science. But yeah, like I said, we're not going to be shooting down missiles with this.
Absolutely. Now, and I know that this is a system that's already smaller than other facilities that can come close to creating X-rays. But is there a miniaturization future for this type of technology, or is it too soon to be thinking in that way?
I think that there is, that the laser technology that's necessary to drive these sources is advancing very rapidly. So, for example, I could see this conceivably being adopted in even things like the security screening at airports. It's not going to happen during the next 10 years, but maybe in 20.
So is it because the power of the overall profile of how much energy you're putting into the subject is low that it would be safe for something like security, or are you talking about just for zags?
That's right. It's only generating X-rays that are emitted in the direction where you need them. So it gives some very significant advantages.
And of course, for a medical X-ray or for radiation therapy, and this would be in the future, not at the wavelengths we make, but at harder X-ray wavelengths. But it would be very nice if you had a directed laser-like beam and not X-rays everywhere, because essentially the X-rays in the security line or in your medical in your hospital or dentist office are essentially X-ray light bulbs. The light goes everywhere, and that's why the technician has to hide behind a wall, and you have to put on a lead apron to protect your body from except for the part that you need to be imaged.
Right. Very cool. All right, great. I'm going to wrap this up in a couple seconds, so if anybody else online watching has any further questions, just go ahead and get them to webcast@nsf.gov quickly. And in the meantime, a lot of people have been asking actually about applications, but then what comes next? Where do you see your research going next? Where do you see the technology going next? And Neil McDonald actually had asked about how soon can folks see these things in the marketplace to use them for their own technology work or for laboratory work?
Probably in short term, currently we are prepared to use our X-ray laser pulses to study and understand better energy harvesting, for example, for more efficient solar cells, when also at the current moment we are ready to study magnetic materials, for example, to explore the limits how fast we can store data on our hard drives. But in a little bit longer term, and what we want to do is to explore the limit how short can be the X-ray wavelengths. And for example, currently we are in the so-called soft X-ray region of the spectrum, and we would like to see if we have a chance to make a better medical X-ray device. we have a couple of advantages versus the current technology. First is our X-ray pulses live for a very short amount of time, so then the radiation dose will be minimized extremely. And the second advantage is as Margaret mentioned, our X-ray beams are really well directed, so we'll be illuminating very small area of the human body. So this will, any potential damage will be also extremely minimized. And probably for a more fundamental point of view, we would like also to see how fast we can make these X-rays. Currently, they are faster than the motion of the electron. These are the attosecond time scale, so we can make movies of the electrons. Next, we would like to see if we can go into the zeptosecond time scales, and these are time scales of processes that happen inside the nucleus, interaction inside of the nucleus, and so probably these are the next steps.
Yeah, and I would add that as laser scientists, the thing we want most of all is to see the technology that we develop be used by other scientists and also in the commercial marketplace. And in technologies that Margaret and I developed in the past, we have brought to the marketplace through our own company so that they would be accessible to scientists. And we're certainly aiming to the same here, to really make this technology available and to see it broadly used. And just like in 1960, after the laser was first demonstrated, a lot of people said it was a solution looking for a problem. And now 50 years later, lasers are used in everything from eye surgery to the internet. We can see a similar development of applications for this coherent X-ray technology.
That's great. Margaret, you want to add anything to that before we close?
No, I think Henry summarized that well. So thanks,
Perfect.
John.
Sure. So thank all of you. Tenio, Margaret, Henry, thank you very much for joining us.
Thank you, Josh.
This webcast, absolutely, thank you. This webcast is being recorded. It will be available, I'm told, probably about 5 o'clock today. So if folks need it, just give me a call. And with that, thank you for joining us.
Bye-bye.
Bye-bye.
Bye-bye.